Okay, before I do the next example, I just want to show you here the algebra rules for doing sums. So if I have the sum as k goes from 1 to n of a sub k plus b sub k, so these are like two different formulas, the a sub k and the b sub k. I can just break this up into do the sum as k goes from 1 to n of a sub k, and then add to that, when I'm done with that, the sum as k goes from 1 to n of b sub k. Likewise, if there's a minus sign, I could do the same thing. If I have a constant in front of each term, that would be like multiplying the constant times each term, so I can just pull the constant out in front of the sum, do the sum first, and then multiply the constant, because that's like adding it. That's like multiplying it times each term anyways. And notice that if I have the sum as k goes from 1 to n of c, that's like adding c up n times, right? Because when k is 1, I get c. Plus, when k is 2, I get another c. Plus, when k is 3, I get another c, out to n. So in other words, I have n of those c's, which is n times c. Okay. This one I want to show you. This is a famous formula. We actually have a couple famous formulas that I'm not going to derive actually three famous formulas. I have the sum as k goes from 1 to n of k, which I'm going to show you here in a second why that's n times n plus 1 over 2. I also have the sum as k goes from 1 to n of k squared, and as k goes from 1 to n of k cubed, which I'm just going to tell you what those results are in just a minute, but they're a little bit more complicated to show, but this one's pretty easy, so I want you to see it. So notice that if I take the sum as k goes from 1 to n of k, so that's 1 when you plug in k is 1, plus 2 when you plug in k equals 2, plus 3 when you plug in k equals 3, all the way out to n when you plug in k equals n. So that's one way to write it. Now, when I add up these n numbers, it really doesn't matter if I add them up in the reverse order, right? So another way to write that is to say it's this n plus the previous one plus the next previous one all the way down to 1. So I'm just writing them in a separate order. But notice now, if I add these two together, it gives me two of those guys. Two of the sum as k goes from 1 to n of k. And then look what happens when I add each term. Each term is n plus 1, right? n minus 1 plus 2 is n plus 1. n minus 2 plus 3 is n plus 1. The next one would be n plus 1. 2 plus n minus 1 is n plus 1. 1 plus n plus 1. So essentially, I have two of these sums equals n plus 1 times n plus 1 times, well, how many of these are there? There's n of them. Remember, we start with n numbers. So there's n times n plus 1. Then I divide by 2. So there's my formula for that. So it's just a formula. I just wanted to show you that's actually a proof. I didn't want to tell you it was a proof and freak you out, but that's a proof of that formula. And then on the next page, there are two more formulas. So at this point, I would just say, hey, write these down in your cheat sheet if you ever need them, right? But the sum as k goes from 1 to n of k squared is n times n plus 1 times 2n plus 1 all over 6. And the sum as k goes from 1 to n of k cubed actually ends up being, so this guy looks like k, right? n times n plus 1 over 2, but I actually have to square it, okay?